professor here at Wolfgang, and today in the first installment of the computing seminar series, we have Seth, Wolfgang, and Skyler Ruiter talking about their research. Go ahead, guys.
Once again, thank you so much for attending. My name is Seth Wolfgang, and this is Skyler Ruiter. And today we'll be talking about our research that we've been working on for the past year and a half, and it's a small solution for big data. And so, just to start off with a little bit of background here, data is getting really big. It follows a very similar trend to Moore's Law, where it's doubling every few years. And so, as an example, we have the human cell census, which is a big genomics data set. It takes 680 gigabytes to be stored in a compressed format, and that's just not economical. You often have to offload that to AWS or a high-performance machine, and that's expensive. And so we need new techniques to handle this kind of data and handle it efficiently, and compression is just one way to do that. And so there are two main characteristics that we want to focus on, and that's high sparsity and high redundancy. And what that means is we want relatively few non-zero values, and we want those values that we do have to be repeating. And so when we have this kind of duplicate information, that gives us a great opportunity to compress. And we have a major use case, which is genomic data. So this is useful in science and industry. And our current attempts at taking advantage of this kind of data don't work very well. They mainly focus on sparsity as opposed to redundancy. And so over the next 10 years, we're projected to get about 40 exabytes of genomic data because big companies like Apple and Shane Zuckerberg Initiative are trying to collect this kind of data for use in research.
It's really important to get a sense of that scale. It's really, it's hard to get your mind around such a massive scale of data. 40 exabytes. A single exabyte is 1 million terabytes of information. And so if you're needing to compress that, you're in a decent business. So there's just so much of it to compress, and for moving forward with new abilities to get genomic data and transcribe it and being able to use it more efficiently with new technology, we've now entered a space where we can work with this data more efficiently. So now we're working on that.
And so how is sparse data typically compressed? Well, start off with, we need to focus on what a matrix is. So you might have seen this in high school, or if you've taken linear algebra. It's a mathematical table to hold data. In code, you might see this as a 2D array, and this format that I have listed here is a dense format. So it's really great at storing dense data, but we're focusing on sparse data. And so a sparse matrix is going to look something more like this. This is coordinate format. So what we're doing is we're storing the row, the column, and the value, and we're removing all the zeros. So in many computations, we would quite literally be multiplying by 0, and that's both a waste of RAM and it's a waste of time.
And obviously this matrix is not, very sparse. There's only a few zeros in here. We're more thinking about a matrix that, you wouldn't use a sparse matrix for like a 5x5. You would use it on a matrix that has, a million, thousands of rows. You would have, 80% sparsity. Most of those values would be 0.
And so how would we compress this further than a coordinate format? Well, so in coordinate format, you'll see here, this is a different matrix than what I showed before, and you'll see that in our column array, it's all zeros. So this is just the first column of our matrix. And so this is really redundant. It's a waste of space. And we can get rid of this by recording how many non-zero values we have in this column. And so that's the basis for a compressed sparse column, or CSC, which is a very mature and widely used format. It's in pretty much every sparse matrix library. And what we're doing is we're ordering each of the values by their column, and then we're also only storing the start of the column. And we have 11 values in here, and you'll see in the column pointer we have 11. That means that's how many values we have in this column.
And just think about how much compression you're really getting here, just with these simple changes. You're going from just storing where the coordinates are for points to, okay, let's order them by column. And now let's just store where each column starts. That is, close to 30 to 40% savings over that previous format. That's just a simple change that you can make.
So we're storing 24 out of the original 33 values. And columns compression. So we can still do a little bit better while keeping it readable. And so our duplicated values, they're just all redundant, and we can compress those. And so we can group the indices by their value, and this is a dictionary where our keys are the values, and we're grouping all of our row indices together. And so we're going to reorder those and keep all associated row indices with their values together. So in the green we have the 1s, in the blue we have the 2s, and in purple we have the 3s. And so what we're going to do is we're just going to drop all those redundant values out while still keeping everything ordered. And instead of that, we're just going to store the counts. And so you'll see here, we have value compressed sparse column, or GVSU,
which is our first format that we've created.
And so, since we're only storing unique values in the row counts and the row indices, we would repeat this for every column in our matrix. And then, in this example, we're only storing 19 out of the original 33 values.
And I know it can be a little hard to see up here what's the numbers, but if you can see them, you should take a second just to, okay, that's the numbers. Prove to yourself that you can take these values and reconstruct that dense matrix. Not the one from previously, but the dense matrix we're representing here. You can go and you can see that we've got 4 1s at 0, 1, 13, 15 in the first column, since that's what we're looking at here.
And so, how can we do it even better? Well, right now, we're only compressing zeros, so we use the recording format. We compress the column with compressed sparse column, and we just compress the values with value compressed sparse column. And so that leaves a little bit more room for improvement. You'll notice that this matrix is a little bit different. I changed the values of the row indices so they were all larger. And right now the rows aren't compressed. So what can we do about that? Well, we have 2 methods to improve that. The first one is positive delta encoding, and then we'll use byte hacking.
And these 2 formats are what make up our next compression format.
And then for simplicity, we're just going to focus on the row indices associated with 1. So what we're going to do with positive delta encoding, if you'll notice in the bottom right, I have a little table there to show the limits that each amount of bytes can store. So the maximum amount of, or the max value you can store in 1 byte is 255. And you'll notice that the last 2 values in our array are greater than 1. So what we can do about that is, right now it's just 8 bytes total, so this is going to be 2 bytes for each value. So what we can do about that is we're going to look at this as a byte level view. This isn't quite binary. You can think of it more as a bucket. This is the size of the bucket that we need to store these. And we're just going to take our current index and we're going to subtract the previous value. And so this is positive delta encoding. If you look at the 49 in the bottom row, you'll see that is 50 minus 1. And then for the 256 became 206 because we subtracted 50, and then so on.
And so if you wanted to reconstruct the original from your deltas, you would just work your way from the start down, adding your deltas up to get your values.
Yep. And so what's really cool about this is that they all fit in 1 byte now. And so we'll use byte hacking to compress this. And it's really simple. We just remove the bytes with a 0. Where all these are being stored in 1 byte. And we just have the amount of memory that's needed. So to put all this together, we just have our unique value and our row deltas, which is what we're calling our new compressed row indices. We're going to record the size of each row delta, which is 1 byte right now. And we're just going to put everything together. So now we have our value, followed by our byte length, and then our row deltas, and then we have a delimiter at the end, which is basically a period. It says this is the end of our value. And this is really cool because we can repeat this for every unique value and every column. And this is the basis for the second of our new sparse matrix format. And it's called index and value compressed sparse column. So this is the same data as what we had in the table earlier, except now it's compressed in every aspect. So we compressed our rows, zeros, our columns, and our values.
It's important to remember that this is also just a little toy example, just for looking at the compression techniques behind it. This would be applied at a massive scale. So this little granular ability to compress unique values within columns and use all of those row indices to compress, you would be looking at thousands of them at a time. So you'd be able to compress much more than you'd be able to even see here and us represent here in just a slideshow.
And so what's really important about this is that while this is really compressed, it's still usable. I don't need to unzip it or decompress it to be able to read this. And that's really important because it allows us to keep everything in a small amount of memory while just still being able to use it.
And how much faster is that faster memory than your hard drive?
Well, if you weren't to compress this, it would be stored in your hard drive, which is about 2,000 times slower than your RAM, and that is a huge performance boost. And so just to compare to value compressed sparse column in the previous format, I have a reordered one array that's it's the same thing, just longer, has the same data. And so if we compare this to index and value compressed sparse column, it's visibly much shorter. So instead of storing the original 33 values that we saw with the coordinate format, we're only storing 11 and a half. And that's a massive improvement overall. And so you might ask yourself, well, that might mean that they're slower, and there's usually a balance between performance and compression. And we'll talk about performance in a second here, but it's important to talk about redundancy, which is the main aspect of what we're compressing on.
Yeah, so if I give you a matrix, I ask you, how redundant is the matrix we're looking at? You're just going to tell me, it's pretty redundant. I need a number. I need you to tell me how redundant the matrix is. So we need to define it. Well, where should we start defining matrix redundancy? Well, maybe let's start with an intuitive definition of, just number of non-zeros over your number of unique values in the column, which is essentially just 1 over your average number of repeats in the column. Simple enough. And then you go ahead and do 1 minus to make it a nice bound between 0 and 1. Simple enough. Well, we tried this, and we used this metric, and we didn't think that it showed enough granularity at higher redundancies. It just wasn't able to show us the results that we were looking for when we were trying to dig into those higher redundancies. For example, if you had, a very large data set, 1 million non-zero values per column, and 100,000 of those were unique, the natural instinct would still put that at a level of redundancy. You might still say it's redundant, but we wouldn't really consider it for that type of data. We would say it's not redundant enough for the type of data we want to be working with. And so we developed a new format, a new equation to model redundancy. The weather's scared me. And so this formula defines the difference in magnitude between your non-zeros in your column and the number of unique values in your column, and it has the unique property of being able to give us a high resolution image of redundancy, while also being able to adapt to the size of your matrix, which worked incredibly well for our purposes. You can see here in the graph, you have unique elements on the y, non-zeros on the x. You can see as you work your way down there, as you more redundancy, you just end up at around 0.8. Well, now that we have a way to measure redundancy, you're going to see that we're in a lot of the next few slides. How well do we perform? How fast are they? That's the whole point, right? We made them small, but now we actually need to use them in core and make them fast. Well, first, how small are they? Just how much can you fit in your RAM? Well, for CSC, you can see here we have a similar looking graph, but instead of now coloring on redundancy, we're coloring on our memory cost over dense, with still unique elements on the y and non-zeros on the x. You can see that those bars, they do not change as you change your unique values. CSC doesn't take advantage of that, which is, where we're trying to improve. So first, CSC. You can see, obviously, a difference. It's tilted. Great, perfect, we did what we accomplished. We are leveraging redundancy to compress. Well, IVCSE compresses even deeper than VCSE does, at the cost of speed, obviously. So you see that shift here. You see the line shift upwards, denoting a higher degree of compression for this format. Well, let's look at a graph maybe, where you have all of them together. So we basically took a sparse matrix, fixed the values in it, and then changed the values as so we changed them to be more or less unique. So we get ultra redundancy and graph it that way. And so here we're looking at a 1 million by 10 matrix that's 90% sparse. You can see along that little flat line, that's CSC. As we'd expect, it doesn't change as you change redundancy. But as you'd also expect, we do. You can see VCSE is that blue line, just levels out at the higher ends of redundancies, and then at the bottom there, you see IVCSE. Well, what are those little bumps in? Those are weird. That's white packing. Those things that that stuff that Seth talked about earlier with the buckets and pushing all of those indices into the smallest container you can fit them in. These are the levels of redundancy you need to get to those lower buckets. So once you go from one bucket size to the smaller bucket size, you've improved your memory usage by enough where you can see it on the graph. And so looking at a couple of real-world data sets, let's take a look at a few real ones. So the first one you see is like a social networking one. The second one's movie lenses, movie ratings. Well, the third one is that's a PDE equation, a partial differential equation, highly non-redundant. It sucks for us. Flat out, we're not good for this data. That's because it's not redundant. You need high levels of redundancies for our data, otherwise it's not a good format. You should use CSC instead. But as you can see for single cell in Web of Science, which is a bag of words modeling next to machine learning applications, we're doing great. VCSE is coming in 60 to 70% of CSC size. When you're talking about 680 gigs, and you're saying 200 gigs of data or something on those lines. If you're going to IVCSE, you really need to fit it into small amounts of memory. You're getting really good savings for single cell data in particular, going down to 12, 13% the size of your CSC size. Let's look at time to construct. All that stuff Seth talked about, you don't get it for free. You gotta do it. You gotta do it in code. Like Seth said, there's a dictionary involved and all kinds of stuff. So how long does it take? Well, CSC, you're pretty fast. There's not a whole lot going on that you need to be all complicated with, so you can make a CSC matrix like that, blazing fast. But, as you can see in the graph, with time on the y, redundancy on the x, as we increase our data being more and more redundant with that same type of generation of the data we saw before, where we changed single matrix to be more redundant, we're faster. So you get more speed and more speed and more speed the more redundant data is. So the better your data is for our format, the better our format works. Well, how about iterating over a column, per se? A very important metric for if you need to go over your entire data set, and generally determines how fast you're able to work with your data. VCSE is, we're fast. It's fast. It's about as fast as CSE, especially for that redundant data, which is where we're looking to be. IVCSE, all of that byte packing, all of positive delta encoding, as I said, you don't get it for free. It's a bit slower, but not unusably slow. It's still plenty usable in plenty of applications. And if this is the difference between putting it in core or putting it on your 10-year-old hard drive, it might be worth it. Well, let's look at some more concrete examples of speed and performance. First, scalar operation. Taking the matrix, multiply it by a scalar. Man, VCSE, very impressive events. Faster than CSC at times, depending on how redundant the data is. And you can kind of think about that too intuitively. You have your values, only unique values stored per column. So when you're doing a scalar multiplication, all you gotta do is you look at your unique values and multiply them out. For CSC storing, every single value, no matter what. So if you have more unique values than you have non-zero, or less unique values than you have non-zero values, you can iterate over that potentially faster. You see that reflected here. IVCSE, a little slower, because you can't just jump into the data wherever you want. So you have to kind of work through the indices as well. So it's a bit slower to do so. But again, not unusably slow. Going into sparse matrix vector and sparse matrix matrix, very important sparse matrix operations for us to be looking at. CSE, it beats us out of the water a little bit, but obviously it's going to do so. It's much, much easier to use. And, you know, you might be thinking, well, VCSE's got that fast iterator. You're going through it at lightning speeds, comparable to CSE. Well, remember how we ordered by value earlier? We cannot order by indices anymore. It destroys your ability to work through that dense vector, that dense matrix. You can't cache that information out because you're just jumping. You're jumping all over the place because now your values in your sparse data aren't ordered well. Makes it a little bit slower, but we tried our best and still got it pretty fast. Well, let's take a look back at what we talked about format-wise. We're just going to take a look at the bigger picture. You know, you can see that CSE, you're only compressing the zeros and column indices, and you're kind of funneling more compression as you go deeper. You know, VCSE, you're getting those repeat values. IVCSE, you're getting those row indices. And then that comes with the trade-off that we mentioned earlier. It's slower the more you compress. Generally, you saw some exceptions today. So depending on your data, you might get it basically free. But generally, slower compression, or slower read speeds, but better compression, which, as we mentioned earlier, you can put it in memory, and now it's faster anyways. So it's very dependent. And obviously, we need it to be on sparse, but more importantly, redundant data. If it doesn't have redundancy, it's not for us. That's for CSC to do. Okay, well, what's next? What's next for IVSparse? Well, first, AI and ML, the big buzzwords, the things that everybody's looking for. AI and machine learning. So first, we want to support the ability to do AI and machine learning with these types of data. So as you know, genomic data comes into fruition as a bigger and bigger topic for research in computing and bioinformatics. Being able to use data smaller, more compressed in AI and machine learning routines could be very important. You can fit more of that data, as we've mentioned before, in fast memory. So it's way faster. There's a proof of concept you'll see here at the bottom. We enable a non-negative matrix factorization, where if you are familiar with Dr. De Bruyne, you've probably heard that term before. And you train a 5.6 billion parameter model. That's a lot of work. But essentially, we tried it and it worked well. And so we'd like to just finish out by acknowledging some of the people who got us to this point. Starting with Mark Clennell, who helped us a lot with the ability to write our code and help us with the redundancy. And then, obviously our advisors.
I'd like to thank Dr. De Bruyne and Dr. Aaron Carrier, whose mentorship has been invaluable this whole time. This project would not have been possible without them in basically every step of the process. And I would also like to thank our HPC team for their help in allowing us to benchmark. And then our funding came from the Shane Zuckerberg Initiative and the Van Andel Institute.
And I would like to answer any questions you might have about our work, about our research, and about our data structure.
Yeah.
We can go around.
Oh. Much
Round
appreciated.
of applause for Dr. De Bruyne and Dr. Aaron Carrier.
Yes, Dr. Lally.
So, can we go back to some of the results graphs?
Which one?
Any of them. So my question sort of applies to all of them. For some of these, it seems like your measurement would be a little bit stochastic depending on the particular data that you're looking at. So are these lines averages? Are they medians? Do you have a sense for what your confidence intervals look like on them?
So these are averages.
Okay. Do you have a sense what the variance looks like for these measurements?
I don't believe we do.
That would be interesting.
That would be interesting.
Just in terms of reporting your statistical thing.
Yes, Dr. Sherman.
Are these sequential operators?
Yes.
Might be a good idea to try this out.
Ah, yes, you're right. That's also
That
something.
is actually one of the future plans is to start incorporating more multi-threading. I don't know if a GPU.
None of these in here are parallelized. We do have some basic parallelization involved in the library itself, just for basic parallelization or trivial. But it's not a topic of our research in particular because there wasn't enough of it for us to really, have a substantive amount of it.
So in terms of putting this in application, I'd like your acknowledgement of sort of the trade-offs, right? Sometimes it's better and sometimes it's not, and that's dependent on the type of data.
Yep.
If I'm a researcher, that has never sat and talked like this, but I see this available, what would be the feasibility of a tool that would sort of scan my data and recommend which is the best one to use to?
We have, so there's a few things that we've looked at that could be interesting there. We were reading a paper by Dr. Ortega who made essentially a profile. We would look at the data and try and classify it, but it's difficult to try and classify it. You try to use machine learning to classify sparse matrices to use different solvers, but it's difficult to do so. That's kind of why I made VCSC in a way, is to kind of have that middle ground where you might not be sure your data is redundant enough to benefit on IVCSC, but you might know something that your data is decently redundant. Sparsity is not that hard to check. You can check the sparsity pattern on it. And so you can still use VCSC, which is still pretty performant in comparison to a CSC format, and then go, well, I'm getting good savings, or I'm not getting good savings, it's fast or it's slow, and you can use that as kind of your benchmark between one or the other and try and help you move. Is that?
Yeah, I was just thinking, I noticed that you've got plans to put it in the sci-fi and things like that.
Yep.
It's kind of nice ahead of time to have that sort of, yes, we should use it, or, hey, we tried our best, but you're not the right ones for us.
Yeah.
Just kind of a usability.
We do try and be decently clear in the documentation we have. Right now it's just C++ documentation. We're still working on the other parts, especially getting into SciPy and getting into there, but that's future work for right now.
Yeah.
I know you mentioned the cell census data compilation or whatever. And this would work as a general solution, but did you have specific data sets in mind that tend to have high redundancy?
So things like classification. So movie lens, for example, let's say you have a whole bunch of movies and there's only so many categories. So things like that.
Or our bag of words model, where you're seeing a lot of repeat words coming in, or a topic of documents, you'll see a lot of repeated topics, something along those lines.
So how many times you see the word the in the page?
Genetic data just happens to be like the shining gold star in front of us. That's like, what an amazing place for us to jump in and work with this type of data, because it has a lot of ability to leverage the characteristics of it. Anybody else? Anybody brave?
Sure. So you've got a big audience of lots of students. So can you talk about some of what were your biggest challenges when you were doing this research, and how did you push through and overcome?
Oh, the biggest challenge.
So
Everything.
I haven't.
Well, I started not knowing what a vector was. So we started there. We started at the bottom. The hardest part for me was building a library for others to use, like actually for realsies use. That's not something we're taught super well through the course load, and actually having to have Dr. DeBruyne and Dr. Carrier go, why would you ever use that? Or who would ever use something that works like that? And going, maybe you should change that. That kind of stuff. Making good documentation. And this was in a language that I didn't know, C++. I was, a Java user up until that point. and I made the thankful change over to C++. And being able to just use a lot of those concepts from the language and being able to make a library in that language while learning it was definitely the hardest part for me.
There's another part of that too. It's just perseverance. You know, I came into this project being confident and then quickly being like, hey, I don't know anything.
Yeah,
And
imposter
so,
syndrome.
After a couple of weeks, I started learning more and more, and I was like, okay, this makes sense, and it's just persevering through everything and as you go. The weather's still scary.
Well, it's all melting off the roof right now and falling.
I suppose an intern might feel the same way. It's just persevering through everything, and I think that's what a lot of research is.
It's pretty fun though.
Yeah, it was really fun, just having a lot of freedom to do what we want. We still had to have an end goal, like, hey, this is what the user needs, but there's a lot of freedom. Yeah.
Question. So nothing here was optimized for any sort of parallel algorithms.
No, we're focusing more on sequential implementation just to start off with.
We're focused more on the data structure in particular.
Sure. Was there any comparisons done between how this quantities algorithms that might run in parallel?
The main thing we compared against was the eigen library, which does, use a lot of techniques to make itself faster. We ended up in here at least pulling all of eigen's ability to be out ahead of us for things that we weren't taking advantage of either, so it'd be more of a fair comparison just against CSC. But in terms of just being able to go further with parallelization, there's kind of mixed results depending on what you're doing. I forget a good chunk of what we were doing because we kind of left that road back a little while back, but.
Is the advantage of using something like this as opposed to using GPUs and something fast like that because of the space then?
Yes.
Because that being limiting for the other algorithms that we're running in parallel, they wouldn't fit everything in GPUs there.
So basically, if your data doesn't fit in memory and you really don't want to load off to the hard drive, this is where it would come in.
There's also like a trivial parallelization thing where since we store each column separately, you could just do it across columns, and that's the main thing where it's like, it's parallelized across columns.
Parallelization is in the future. What we have right now is quite simple, but it's still like a future plan.
It just gets a little bit weird because we don't have indices that are ordered. And so that obviously throws a wrench into some algorithms and the ability to take advantage of some ability to caching and stuff like that. Because when you iterate through, random access is essentially throw it out the window. Please do not random access into this data. Because at least for IVSparse, if you wanted to random access into it, you'd have to go to the column and then you basically have to iterate through an unpositive delta encode, unbytepack, and find your way into that index that you're trying to look for. So obviously random access is a really bad operation for these formats, and so some things just don't work quite as well.
Yep.
These matrices are integers.
Sorry?
The matrices that we're working on are integers.
Yep.
We also test doubles, floats, and negatives and stuff like that.
But then the deltas will be different then, or?
I'm sorry, I couldn't hear that.
The deltas that are using the compression scheme, where you have.
Oh.
Yeah, so the results, I believe, are.
He's asking how would delta work if the matrix contained doubles.
Oh.
Yeah, so your value is, it's all recorded like in the same array. We have a little bit of finagling so that we can have arrays of variable data types, if that makes sense. So it still works with doubles, and then you have all your integers after that.
And then another question, in neural networks, these days it's relatively popular to use lower precision floating point numbers, 8 or 16. Would this work here as well?
Yeah, it would still work. Every data type works. So it doesn't matter what your value type is, it would still fit. Any more questions?
So is this a target for publication somewhere? Or
Publication. It's currently accepted as a one-page summary into the data compression conference.
We have a poster.
Yeah.
We were accepted as a poster to IEEE Data Compression Conference.
And we intend to take the rest of our work and publish it into a bioinformatics journal later this year. And so that would require, a more directed approach at bioinformatics instead of just generally the data structure as a whole.
Just curious, those biology databases, or matrices I should say, when I think about biology databases, I think about A, C, D, G, and so on. So these are matrices of numbers? What's the difference? What are
These are matrices of genes and cells, and expression of those genes and those cells.
Yeah, your A's, your T's, your C's, and your G's.
But you don't have really matrices of that.
No, that's a little different. Matrices, G's and T's.
Would this be traceable for that?
Yep.
You got one, Dr. Pellegrini?
But more of a suggestion. So, in addition to targeting a bioinformatics journal, which you absolutely should, 100%, you could also look at some of the journals for open source software. So that's you would just write a paper that's just describing the library that you wrote. And so the nice thing about that is whenever someone uses your software, they have like an obvious thing in sight. Like, oh, I'm using this software package.
Didn't think about that. I like that idea. Thank you very much. All right, we all good then?
Any other?
Oh, we do have a question.
So, possibly like split up and make so there's like some parts maybe more obvious than others. You get
You're talking about like a CSC, IVCSC, like have you. We did think about that.
It may be grant proposals out to hide that.
Yeah.
Going back out, hide that.
So don't steal that.
Yes, there